Hello my dears, now we are going to discuss Jfet as an amplifier, or how can we use this Jfet in the modern technologies as an amplifier, like BJT as an amplifier, right? So what are the how can it be work? How can it be work? I will tell you. For controlling the drain current, we are using an RL in the drain circuitry, that's all. So this is nothing but, my dear, source, and this is nothing but gate, and this is nothing but drain. So for controlling the drain current, because the drain current should not be very high, right? It should be limited. So for limiting the drain current, we are using the resistor RL. That is nothing but the load resistor, or you can name anything. And this capacitor always filters the output. It blocks the DC, and it will definitely, we will get a pure AC content, right? That is why we are using a capacitor. And here we are applying the signal, and this is nothing but our VGS. This is my VDS and this is my VGS. So what will be the nature of the output, we will discuss. When we are applying the signal should be definitely a positive and negative AC, right? Contain a positive and negative AC. So for the positive half cycle, what happened, my dear? This region is nothing but N. This is N channel, and you know this, inside this, here will be what, my dear? P. Inside this there will be P, am I right? Inside this there will be P, am I right? So for the positive half cycle, what happened? Regardless of this VGS as the reverse biased, this VGS definitely makes this P into reverse biased condition. That is the peculiarity of N channel that we already discussed. When we are applying a signal, so regardless of this VGS negative polarity, the signal contains positive, right? This positive and this P will combine together and effectively making the channel width increased. That means when signal applied for positive half cycle of the signal, the P region less reverse biased and increases the channel width, so that ID increases. And similarly, for negative half cycle of the input signal, the P region more reverse biased and ID reduces. See what I am writing. See, my dear, when we are applying a signal, it contains positive and negative half cycle. For the positive polarity, this P and this P got positive forward biased, and in effective the reverse biasing will be reduced, right? So that the channel width will be increased. That means depletion layer will be reduced, so that the channel width will be increased, so that ID will be increases. The drain current will increases. But for the negative polarity, these negative, the signal negative along with the applied biasing negative makes more depletion region. Makes the depletion region width will be very high, the channel width will be very less, so that the ID will be reduces. That's all. Is it clear? Next we have to see the output characteristics of the Jfet. It's very important to note that, my dear, the output curve is nothing but the graph between ID and VDS for constant VGS. So what is mean by output characteristics is nothing but, my dear, output voltage versus output current. Like BJT, output voltage is nothing but voltage across drain and source. Output current is nothing but the drain current. Input voltage is nothing but the gate to source voltage. That's all. So the graph between the output voltage against output current for constant input voltage or VGS is called the output cara. Very interesting thing you have to note from this output cara, my dears, that is nothing but for VGS equal to 0, the cara has maximum current value. For maximum current value, the cara has maximum current value, and that maximum, the current value is called IDSS. The full form of IDS is nothing but IDSS. It is nothing but, my dear, gate to source drain current. Gate to source short circuited drain current. Gate to short circuited drain current, or shorted gate to drain current. Gate to source short circuited drain current or shorted gate. Simply you can use this. It's much shorted gate drain current. Shorted gate to drain current. Shorted gate drain current. It's very important term, my dears. Shorted gate drain current. So let's discuss what is this IDSS in Jfet. See, my dears, whenever we are off the gate to source, that is VGS equal to 0 volt, I already discussed that minimum depletion layer will be there at that time. That means maximum channel width will be there, because no one to reverse bias the gate, no one to reverse bias the P region, so that maximum channel width will be there, maximum current will be flowing. So whenever we are increasing the VDS, a large current value ID we can observe. That is why the curve is top of all the curves. Top of all the curve. One thing, whenever we are increasing VGS, my dear, what happened? More and more reverse biasing will occur in the P region. In the P region, more and more reverse biasing will occur in the P region, so that the channel width will be very, very less. Whenever we are increasing the reverse biasing, the channel width will be very less, so that the drain current will not be that much. Initially it was there, now it is here, now it is here. The drain current start decreasing because the channel width got reduced. The channel width got reduced. And come to the point, IDSS is the shorted gate drain current. It's a very important parameter in the Jfet. So what is mean by IDSS, my dear? IDSS is nothing but, it is the maximum value of drain current. It is the maximum value of drain current. At a pinch of voltage. After that, the drain current will be constant. So shorted gate drain current is nothing but, my dear, maximum value of drain current at a pinch of voltage. So what is mean by pinch of voltage, my dear? The pinch of voltage is nothing but, when VGS equal to 0, when we are operating the Jfet, what happened? There will be maximum drain current flowing, and after a certain value, even if we are increasing the value of VDS, after that there will not be any increasing the drain current. the drain current will be a constant afterward, even we are increasing the value VDS. That particular point after which the drain current is constant is called the pinch of voltage. That particular point at which or after that the drain current become constant is called the pinch of voltage. So IDSS always happens at pinch of voltage. It's very, very important, and which is always happened at VGS equal to 0. These three things will be come together when we are explaining the term IDSS. Okay, whenever we are going to explain the term what is mean by IDSS, shorted gate drain current, we have to come across VP, we have to come across VGS equal to 0. Only by mentioning this VP and VGS equal to 0, there will be meaning for this IDS. There will be meaning for this IDSS. Okay, IDSS. So that's all about IDSS, my dear. It is the maximum value of the drain current at a pinch of voltage. After that, the drain current will become constant. And pinch of voltage is nothing but it is a voltage, particular value of voltage, such that after the voltage, the drain current will become constant. That is called the pinch of voltage. That is called the pinch of voltage. We can't define pinch of voltage here. We can't define pinch of voltage here. Is it correct? Is it correct? So these together can be only explained by IDSS, VGS and VP. These together can be explained, not separately. You cannot explain this separately. You cannot explain here also a constant, now this is a pinch of voltage, here also a constant, now this is a pinch of voltage. You can't say like that. You can't say like that, my dears. You can't say like that. So pinch of voltage can be only defined at VGS equal to 0. IDSS can be only defined at VGS equal to 0. That means the three things come together, you can explain, not separately. Not separately. Is it clear? Is it clear? And I am asking you one thing, my dear. Why this region is a constant current? Whenever we are increasing VDS, there will not be any flow of current here. Why? 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 Because at a pinch of voltage, my dear, there will be a maximum flow of current. Maximum flow of current. Whenever we are even if we are increasing VDS, that means this current is actually constituted by certain width of the channel. Even if we are increasing the drain to source voltage, is anything happen to this channel? Is anything happen to this channel, my dears? Is anything happen to this channel? Nothing will be happen. Nothing will be happen. Nothing will be happen. Okay. Is it clear? Nothing will be happen. Because the channel width is permanently at a particular width now. Even we are increasing the channel width, K to drain to source voltage, there will not be increasing the channel width. You assume a certain example. In a marriage function, suppose it's in a very big temple, you might have noticed one thing. Whenever after the tally, after the tally function, what happened? The bell will ring or someone will announce that food is ready. We'll rush into the auditorium, basement or wherever the food is available, and there will be a small gate. Even thousands of people waiting there on this side of the gate. The gate width is a specific width, right? Suppose 10 or 20 people maximum can pass at a time. Even if we are there, even if there 1,000 people, 1 lakh people, if any more, anything more can be passed by this gate? No. Only 10 or 20 people can be passed by this gate because its capacity is that much. The similar thing will happen here also. A gate having, the channel having specific capacity, the width is the channel in such a manner that it is so and so. So it cannot allow more and more an electron at a time, so that the current will be, the current is always rate of flow of charges, correct? So the current will be always constant because the gate width, the channel width is constant now. The channel width is actually controlled by the VGS. If VGS is constant, the channel width is constant after a certain value. Is it clear, my dears? And one of the very important peculiarity of this Jfet compared to the BJT is there is no thermal runaway. There is no thermal runaway. There is no thermal runaway of Jfet. Why? Because thermal runaway is nothing but, my dear, whenever we are increasing in BJT, I will tell you that what is thermal runaway. Due to some reason, the collector current is increased in a BJT. That increased collector current will increase the region temperature, right? Increase the temperature of the collector region. That will again leads to what? Increased current, because whenever we are increasing the temperature in a semiconductor, so we are not the conductor, okay, consider for the conductor. Large amount of electrons are there already in the collector region. Whenever you are increasing the collector current, what happen? More collector current will increases the temperature. Increase the temperature. That increased temperature will again leads to more and more new electrons to generate. That will again bombard each other. What happen? Again increasing the temperature. So this increasing temperature will leads to what? A final destroy of the transistor. That is called the thermal runaway of the transistor. But in the case of a Jfet, my dear, since the channel width is limited, since the channel is in specific limit, there will not be any increase in current beyond a particular value for very large extent. Not equal to the BJT, but very higher than the BJT, it can limit the current. Only after that, very high voltage, the breakdown will happen. And that also a breakdown, not the thermal runaway. So there is no such a thermal runaway in the Jfet because the channel width is limited. Even though we generating more and more carriers in the channel, the channel width, it will allow only a particular number of charge carriers, so that the current will be always controlled. And another important thing is that this Jfet is a negative temperature coefficient or negative resistance because of negative resistance of temperature or negative resistance of temperature. That means whenever we are increasing the temperature, the resistance is actually reducing. In the Jfet. A reduced resistance means bombardments of the atom will be reduced. Why resistance is increased in a conductor? Whenever we are increasing the temperature, more and more carriers will generate. They will bombard again. The bombardment rate will increase. The relaxation time, in other words, will be very less, so that it will hit each other. It will hit each other in very random manner or very rapid manner, so that the overall temperature will be increased there. But here, whenever we are increasing the temperature, the resistance will be reduced. Resistance will be reduced means that charge carriers will get enough time to collide. It is not that much fast. It will relax and collide. That means there will not be much temperature rise in the Jfet. Okay? Is it clear, my dears? Is it clear? Okay. And so that's all about the as an amplifier, and output characteristics of a Jfet.